All right, welcome to the first screencast for your quiz review. These are going to be, there's 4 questions, they're going to be done in 4 different videos. Maybe I can squeeze the second one into one of these, but the first couple of problems here, A, B, and C, were actually already done on the very first screencast I did. So if you look under the date from the other screencasts with the point ratio form, that will also, well, this is going to look very familiar. So, sample of radioactive material has been decaying for 5 years. 3 years ago, so that means after 2 years have passed, there were 6 grams of material, so I'm just going to write that down as a point. And now 5 years have passed, and there are 5.2 grams left. So to find the decay rate, we first have to put this in point ratio form and find a ratio, and then we can find the decay rate from that ratio since we're just given 2 points. So for A, and again, this is going to look very familiar. We have our 2 points. We have x and y, and then x1 and y1. And so we have 6 equals 5.2 times b, which we don't know, to the 2 minus 5 power. So I'll divide both sides by 5.2, and I'll have 6 over 5.2 equals b to the negative third. So we solve this power equation by raising it to the negative 1/3 power. And then we put this whole side in the calculator and then find out that b is equal to 0.953. So this is the ratio, and if you recall, in order to find the decay rate, we have to subtract that from 1. So 1 minus 0.953 equals 0.047. So the decay rate is 4.7%. And that answers question A. How much radioactive material was initially in the sample? So that's part B. That's our starting point. That was also shown in the other video, but I'll go over it quickly. So let me just erase this to get on to part B. So that 0.953 is going to come back into play because we're going to need to write an equation. We almost have to do part C before we do part B here, so I'm actually going to jump into that, pick one of my new fancy colors. So I'm going to actually jump down to C first and write an equation to model the decay before I actually figure out how much was in the sample. So C, an equation, I'm just going to use that point ratio form. So y equals, I'm going to start with the 6 times, that ratio was 0.953 to the x minus 2 power. So this is our x coordinate here with the 2, our y coordinate over here with the 6, and then the ratio that we found in A. So this is actually C, and now I'm going to use this equation to help me figure out B. So how much radioactive material was initially in the sample? So initially, when we start out, no years have passed, which means that x equals 0. So I'm just going to plug this in here to find out how much was initially in the sample. So y equals 6 times 0.953, 0 minus 2. Throw that all in the calculator, calculate, and find out that it's about 6.61 grams initially in the sample. And that's part B. So we've done A, B, and C. And now, again, that was from that video, point ratio form. If you want to go back and watch that, if this was a little too quick for you, not enough in depth, you can go back and watch that video from Monday or Tuesday. So D, how much radioactive material will be left after 50 years? So again, now they're just giving us another amount of years. So instead of x being 0 like it was in B, now x is going to be 50. So again, I'm going to come back here and erase. I'm going to keep this equation because I'm going to need to use it again. So now, for part D, x is going to equal 50 years. So 50 goes in here, so I have y equals 6 times 0.953 times 50 minus 2. I do all my lovely calculations and find out that this comes out to equal 0.595, so about 0.6 grams are left after 50 years. Easy enough. Part E gets a little bit more in depth and asks a different kind of question. What is the half-life of this radioactive material? So again, let me go back and erase D, and if you need to, pause, rewind, go back if you need to go back to any of these other questions that I've gone over if I've gone a little too fast. So for E, what is the half-life? Well, half-life, we have to know what that means first. Half-life is when is half of the original amount left? Half-life. So at what time is half of the initial amount left? And that's what's called a half-life. So if my initial amount answering in B was 6.61, you could round that to 6.6, let's say, then half of it, so half of 6.6 would be 3.3. So now what I would do here is I would use our calculators to make a table. So we can graph in the calculator and then split screen a table like we've done a bunch of different times. And then we're going to scroll down and look for when our y value, or our f of x value, is 3.3 or less. You could, of course, also take this equation from part C and guess and check. So we could keep plugging numbers into x for different amounts of years to see when y is equal to 3.3. So this is what I'm trying to find out. What would x be in this equation when y is equal to 3.3? I think the calculator is a much more efficient way of doing that. If you recall how to put that graph in and then you just hit Control and the letter T, it makes a table for you, and you find out that it will be half the original size between 14 and 15 years. All right, and if you have other questions about how to put this into the calculator or how to move on from here, then make sure you ask before our quiz on Tuesday or Wednesday, depending on if you're day 1, day 2, and I'll go back over how to put this into the calculator. But this would be your answer to part E. If you plug it in the calculator and make yourself a table and look for when y is equal to 3.3. Or again, you can guess and check, keep plugging in those numbers. All right, I still have a little bit of time left on this one, so I'm going to go on to number 2, and then I'll only have to do 3 different videos instead of 4. So I know it's so blurry, good thing you have the paper in front of you. So number 2, a function f of x contains the points, so there they all are. Give the points known to be the inverse of f of x. So from all of our practice in class last week, and from the other screencasts, we know that to find the inverse of a function, we switch x and y. Whether it's in a point or in an equation, we're just going to switch. So we can label all of these x and y, x always first, right? And then y. So if f of x are all these points, then the inverse, which we notate with a -1 in between the f and the x, is equal to, and we simply just switch our points around, -3, -2, -1, 0, 2, 2, and 6, 4. Now, one question this doesn't ask, but we could answer, is this a function? So recall that functions need to have each input can only have one output, or can pass the vertical line test. So if you like the vertical line test, go ahead and graph the points. Me, I can do either way. If each input needs to have its own output, I look at my inputs, -3, -1, 2, and 6. My inputs or my x values are all different, so even if they all had the same output, that would be fine because each input has its own output. So since all my x values are different, I don't have to go any further, and I would know that this inverse of f of x is also a function. I know that it didn't ask that, but this was a question when we were going over the practice in class, so I figured why not continue to talk about it a little bit. So that's numbers 1 and 2. I'm going to stop this screencast here and go on. You can look for the next one right below it on my website, number 3, and then I'll probably have a separate one for number 4. Okay, see you in a minute.